Hello and welcome. So with this example, what we're going to do is start off with a Cobb-Douglas production function, like a simple form of it, and then we're going to take the derivative of it with respect to its two factors. So we're going to take the derivative of the Cobb-Douglas production function with respect to capital K and with respect to labor L, and thereby we're going to be finding these things. We're going to find the marginal product of capital and the marginal product of labor. So first off, let's talk about what is a Cobb-Douglas production function. Well, Cobb-Douglas production function takes a form of something like this. This is actually kind of like a specific form of it. It's kind of a bit more general than this, but this is the most common form you'll see in intermediate macroeconomics classes. So Y here is output. I've occasionally seen it equal to P or production. However, in some courses, P stands for prices, so you might not see that too often, but you typically see Y output is equal to, and then a function of something, so you put stuff inside of it. In this case, you have capital and labor. Other versions, they might add additional things like oil or, energy. You might add leisure. I don't know how I show leisure. Let's call that leisure. But in the simplest form, you have output or production is a function of, actually, leisure doesn't make any sense as an input for a production function, but that's beside the point. It's a function of these inputs, capital and labor. And you start off with this little scalar in front representing technology. Very often you'll see this just go away. So we're saying technology is constant and equal to 1. But sometimes you'll see it in front of it. And then you'll have the factors, the inputs. So K is raised to the alpha, and then labor is raised to the 1 minus alpha. A kind of a rule with typical Cobb-Douglas production functions is that the sum of the exponents are going to be equal to 1. If the sum of these exponents is equal to 1, then you have a constant returns to scale production function. And there's a few reasons why you might want that with a production function for your, little simple economy model. But this is usually the form your production function's going to take. You might have kind of variations of those exponents floating around. Okay, great. So let's start off by taking the derivative of the production function with respect to capital. So what are we doing? We're starting off with this, with our production function. And the thing we're looking for is going to be how production changes. So that's a kind of a version. This is a version of the Greek letter delta, which I like to call di. So it's it stands for partial. So it's how production changes. So di y, change in y, given a change in capital. So given a change in capital, we're going to see how production changes. So what is that equal to? Well, we're going to take the partial with respect to capital. So we're going to do this little transformation of the production function. Okay, so what's that equal to? Well, it's equal to our production function. It's equal to the first derivative of the production function with respect to capital. So hopefully, if you're watching this, you remember enough of calculus of how to do this. So what's the derivative of the production function with respect to capital? So first off, you look for any exponents above capital, and there's alpha there. So you got alpha, and there's no other capitals in here, so great. So you got alpha times a times k raised to. So you then take 1 minus what the exponent was. Actually, it's what the exponent was minus 1. So alpha minus 1. And then L is just the same as it was before. And this is the form of a Cobb-Douglas production function, so you'll have something that looks like this. We could also simplify this or change the form of this solution to make it more useful to other situations. So hold on a second. So another way to write this is the following. Oops. So I've broken up this k into 2, the 2 k exponents into 2 here. You have k raised to the alpha times k to the negative 1. We can simplify that to the following. this next one's equivalent. And then notice that this portion right here is just the production function. So a k to the alpha, L to the 1 minus alpha, a k to the alpha, L to the 1 minus alpha. So you could replace that with just y. So this is our answer here. So the derivative of production with respect to capital is equal to alpha times y over k. It's also equal to all of these other things up here too. Sometimes we end with this solution here because it's kind of y divided by k is like the sort of the average output, you know, given a quantity of capital. Yeah. And then another way to write this, the first derivative of output with respect to capital, is the marginal product of capital. So this is all equal to the marginal product of capital. What's the marginal product of capital? You know, marginal product, so that's the value of an additional unit of capital. So if you add one more unit of capital to this production, how much extra production do you expect? You know, what's the marginal product? It's equal to this equation right here. And that's it. This is the derivative of output with respect to capital, giving us the marginal product of capital. This marginal product of capital gets fed in later to finding the rental rate of capital. Rental rate of capital is equal to, depends if we're talking about real or nominal, but let's just talk about nominal rental rate of capital is equal to the price level times the marginal product of capital. However, the real rental rate of capital is the rental rate kind of corrected for prices. That's equal to just the marginal product of capital, which we found already. So if you're ever asked, you know, what's the rental rate of capital, that's going to be this guy right here. Sometimes you're given a value of alpha, and you would just plug in that value of alpha. So let's say alpha was 1/2. You know, if you saw a little 1/2 here, and then 1 minus 1/2 is 1/2. So if you saw 1/2, 1/2, you got a nice little CobbDouglas production function, and you have 1/2 times y divided by k. Okay, so let's find the first derivative of the production function with respect to labor now. So we always start off with the production function. So starting off with this production function, what we're interested in finding is how production changes, the change in y, given a change in labor. So we're looking for die y over die L. So you do that by finding the first derivative with respect to labor, that little symbol, that little notation of the production function. So the first part here, you know, there's no labor in there, so that's going to stay completely the same, but this part's going to change. So if you recall the previous problem we just did for capital, or you recall calculus, you got the exponent comes down, and then you have the old exponent minus 1. So 1 minus alpha times L to the negative 1. So after this step, it's just kind of simplification or reorganization to make it look better or to make it more useful. So I'm going to bring out 1 minus alpha to the front, and then L raised to the negative 1, that's just 1 over L, so I'm going to divide this whole thing by L. So we have this form here. The other thing that you notice is that this little portion right here, that is exactly the production function. So we could substitute just the letter y in for this, because that's exactly what it's equal to. So this is it. Technically, all of these 3 rows are our answer, but this is a nice cleaned up version of it. So y divided by L, you could think of that. Remember, L is like the labor force, or maybe even the population. Y is output. So y divided by L is kind of like the per capita output or per capita consumption or production. So it's like the average production. It's maybe like the labor productivity. And then this 1 minus alpha was just the exponent above L in the production function. And all of this is equal to the marginal product of labor. The other thing is that this gets fed into is wages. So the wage rate, the nominal wage rate, is equal to the price level times the marginal product of labor. And then the real wage rate, that's equal to wages adjusted for prices, which is equal to the marginal product of labor. So you can see how the marginal product of labor, this equation right here, the first derivative of the production function with respect to labor, is pretty useful. It gets fed into this wage equation. Yeah, I should stop there. Hopefully this was helpful. Let me know if you have any questions, and thanks and have a good day. Bye.